Okay. Can everybody hear me okay?
Yeah, sounds fine.
Okay. Well, I'm going to kind of continue on with what we were looking at last time, and that was this some new code that I had written called one wire. There's a transmit and a receive. So I thought we'd just kind of look at those. This is new code that's actually going into, it'll be going into Mercury, Penny, and Aussie. And we're just starting to test it right now. In fact, I've got my radio running with it right now. Let's see if it's, I think it's on. Oh, well, if they had anything. I had it tuned to a local station. So, yeah, it's working right now. Anyway, for those of you that might not have listened to the last lecture yet, part of it, let's take a look at some of this code and some of the different Verilog things that you might do. Alright, this particular one-wire module, I call it, this is a one-wire transmit. Can everybody see this okay? Is it clear enough on your screen?
Yep.
Okay. So here we have a module, and it has 1, 2, 3, 4 different connections. Okay, a reset, a clock, the data that we want to transmit, and a single bit called D out of data that we want to send to another board across one of the Atlas lines. And I call this a parameterized module, and the reason is I have parameters in this particular module, and as you know, parameters can be overridden from outside the module from another module. So here I have some values that have certain default values, like clock frequency 48 megahertz, which if I were to put this in Aussie, that it has a IF clock that runs at 48 megahertz, so I wouldn't have to change this. And the data bits you can see is set at 64. In the real case, I override this because we're only transmitting 59. But the nice thing is this module is written in such a way that if I change these values, the rest of the code will work for those values. So one of the ways in which I do that is, let's say that I had let's say I was going to make a counter, and I needed to be able to count for 16. I need to be able to make it count 16 times. So typically in a counter, I'd go from 0 to 15. So how do you determine how many bits, how wide of a register, we're going to make a register, how many bits wide of a register do you make in order to hold a value that only goes between 0 and 15? In other words, 16 minus 1, 0 to 16 minus 1. How do you determine that? Anybody want to answer? Well, there's one way that you can do it, and that is you take the maximum value, the 16 minus 1, which is 15. Well, what is 15 in base 2? It would be 1, 1, 1, 1. So you'd have 4 ones, right? So that would be the biggest value. Okay, so if you've got 4 ones and the rest everything beyond that is 0, then you know you only need 4 bits to hold that value. Well, how could you calculate what size you need? Well, that's where this little function I made up here comes in. And basically you give it the maximum value that you're going to use, and it's going to take that and just imagine it as 1111. Let's say it was just 4 bits wide, 1111. And it goes through a loop, and each time it goes through the loop, it shifts the value right. Okay? So if you shift the 111 right, then you get 3 ones, and then the next time you'll get 2 ones, and then the next time you'll get just a single one, and in the next loop it'll go to 0 because you've shifted it right by 1 bit each time. So it took us 4 loops to get that value shifted down to 0. So that's what tells us that we need something that's 4 bits wide. Well, I can make a function, and functions are good for doing calculations like that. So that's what this function I called C log base 2, C log B2, That's all it does. It just sits there and determines how many bits I need for a particular value. So I like to use this little function, and I'll show you how I use that function. It's really good when you're making parameterized modules. So let's say that I had, well, in this case, data bits is 64. So let's say I was going to make a counter that needed to loop 64 times. Well, I could go from 0 to 64 minus 1, or 63. So if I take that, where is data bits? Oh, here we go. Here I've fed data bits minus 1, which is 63, and it'll come back. That function, now this is at compile time, this is not runtime, this is just a compile time. It'll calculate this value XS based on what data bits is. So if data bits is 64, I get 64 minus 1, that's 63. It'll determine that I need 6 bits. And so XS is 6 bits now. Well, that's nice, because now, if I take that XS, I can go down here, and I can make my counter that I want to go from 0 to data bits minus 1. I know how wide I need it now. I know that it's 6 bits. Well, so I go from 0 to XS minus 1, which is 0 to 5, so that's 6 bits. Okay. Now if I change data bits, it'll automatically recalculate it for me. Okay. Now if I were to put in a value of change this to 59, it's still going to need 6 bits. And if you go through the exercise, you would see that you'd still get 6 bits. So that's what these functions are right here. These clog_b2 are doing. They're just calculating how many bits I need for a particular register for something that I'm going to do. Okay. Now in this case, I actually need this register to go from 0 to data bits minus 1. Okay, so you can use it directly if you wanted to. But sometimes you might just need to know this type of information, and you can calculate that with a function. And you can make your own functions. So here I've calculated some values. In this particular one-wire logic, basically the way this works, we'll go through this again, is after we reset, there's a delay time, and I specify that as one of the parameters in milliseconds. Okay. Then I feed it some sync bits, five logic zeros. So that's what these are. This is from here to here is a logic 0, and from here to here that's a logic 0. And here's what the logic 0 and 1 look like. So for a logic 0, the first quarter of the cycle is high and the rest of the cycle is low. For logic 1, the first 3 quarters are high and the last one is low. So you notice the nice thing about this is it's what we would call self-clocking. You don't need a clock. In other words, every time you have a rising edge, from this rising edge to this rising edge, that's one data bit. We know that that data bit is contained within that time frame. So the receiver can actually, say it's running on a different clock, it can count clocks from the beginning of this edge to the beginning of this edge, and it could say, oh, okay, it takes me 300 clocks, let's say, for this time period, TB. Well, if I take that and divide it by 2 and then sample the data at halfway through this thing, I should know whether it's a logic 1 or a logic 0. So that's kind of how this works.
Kirk,
Yes.
is there a reason you made the data bit 2 kind of time periods long instead of 1, so that it was a total of 3 bits long instead of 4 as you've designed it?
Right here?
Yes.
Yeah. The reason the last quarter is low is because I want to have a rising edge at the end of the time period.
I understand that, but you've only got 1 data bit and it takes up 2 clock periods.
2 clock
where you've
periods.
kind of designed it so that the clock is always the leading clock bit is 1 long. I guess what the question is, why couldn't the data bit be 1 period long instead of 2 as you've designed it? Is there any particular reason?
No, it just gives me a little more margin here, because if I sample in the middle, I've got some margin either side of this. This is just the way I made it. You can make it completely different. And in this particular case, the reason I did it is it gives me margin, and this transmission is not a very fast transmission. I may be only doing this typically maybe 1,000 times a second, a string of data, and I'll show you the string of data. 59 bits, I think it is, for the current version. So yeah, you could make up your own. I just made this up the other day. So this is just
comment.
This is just one way that you could do it.
Kirk, this is Joe. What's really kind of slick about the way you did this is you can apply this to any board that has any kind of a clock frequency on it, as long as that clock frequency is higher than what, you know, what the individual time elements are. Here, like you said, one interval might involve 300 clock cycles on the board that you actually send this thing to. So that's what's slick about it. It can be sent to any kind of a board and be self-clocking.
Yes. That was the purpose in doing it. And that way we only needed one signal wire. So what we're using it for right now, what we're testing is Mercury has one of these one-wire transmitters in it. And what it does is it'll send out the serial number of the board, and I think there's some like ADC overload. It's going to send that, and it can send that information out on this one wire back to Aussie, and then Aussie can use the one wire receiver, which we'll go over, and receive that data. So Mercury can just sit there and transmit this information constantly, and then Aussie can pick it up. And then on Penny, it can do a similar thing. It can send out its serial number and any other data that it needs to send back to Aussie. And we just need the one wire. And then on Aussie, it can use one of these transmitters, and it can send a whole lot of different information to all the boards, and they can all sit there and listen and pick off the information that they want. So that's where the Aussie's sending out like 59 bits of information. Let's see if I can pull it up. I think this is the latest one I have right now. Okay, here we go. Scroll up here. This is in the Aussie FPGA. And so I've defined this transmit data as all these different things. There's PTT out and an address. There's a frequency gets transmitted. And so this winds up, all of this information winds up to be 59 bits. And so here I've overridden that parameter with a value of 59. And then I fed it a reset, the clock, and this transmit data, and then which pin that it's going to go out on. The one that I call command and control, whichever that happens to be on Atlas, which is C20, I think, on Atlas right now. So that's all I have to do to send all that data out to everybody. So Penny looks at this particular line, and it uses the one-wire receiver and grabs the data from here, and then it can just pick off the data that it needs out of that, out of the data that it receives. Same thing for Mercury or anybody else that wants to listen to this. So let's go back. So basically I've made some calculations like Q1. I calculate based on the parameters that I've got right here. I calculate how long or how many clocks it's going to take running at the frequency that's been specified, and how many, and what my what I call my frame frequency. The frame frequency is basically, okay, I got 64 bits and I want to repeat that 1,000 times a second. Okay, so this calculation just tells me how many clocks it's going to take to generate this Q1, and in Q1 I call this time period the first quarter of this cycle. So that's the amount of time it's going to take for the first quarter. So I've made some calculations here. This one is for the first 3 quarters, which is 3 times Q1, or for the whole cycle, be 4 times Q1. And then the low time would be, I've said for this low time here after the sync bits. These sync bits get sent out initially after the delay time, and then they get sent out once every second. so not real often. So you send these out, you send out this low for a greater than 2 bits of time, in which case I did it for 4 down here, 4 bits worth of time. And then you send the 64 data bits, and then you just keep repeating those 64 data bits over and over for 1 second, basically. Okay, then these are just variables that I'm using in this code, and this is for a these values are for my state machine. We'll talk more about that sometime. And these are all this is all RTL code. Let's go down. So this whole always block here running on the positive edge of clock, these all get turned into flip-flops. Okay, D flip-flops typically within your FPGA or ASIC or whatever you're making. And then this is kind of the guts of my state machine. I'm going to tell you a little bit about state machines, even though we haven't talked about them yet. We'll go ahead and talk about them today a little bit here. This one's a little large. It'd be nice if I had something a little smaller to start off with. But okay, I have a state machine, and basically the state machine consists of flip-flops. And let me go find how many in this case. Here it is. I say I have 5 flip-flops. Now why do I say 5? Well, that's because I have 9 states. So in order to hold 9 states, I need to have 5 flip-flops. So I can hold values from 0 to 8 because I have this many states that I want to use. And the state is merely just a binary combination on those 5 flip-flops, the outputs. So this is actually becomes the output of the flip-flops, this OW state. And so you'll on those outputs you'll see values from 0 to 8. And how does this thing work? Well, in this always block I have an at pause edge of the clock. And let's go down here. Here's the actual state machine. So I said if we're in reset, then I want my state machine to go to idle. Okay, now the natural state for idle would be all zeros on the flip-flops, since naturally when you reset flip-flops the Q outputs all go low. So I always make my idle state 0. Okay, because that's the natural way that the FPGA is going to power up, is with those flip-flops cleared typically. So my idle state is a value of 0. But I don't like using numbers for my states, so I like to use names. So this is why I use this local parameter. Okay, so if we're in reset, the output of the 5 flip-flops is going to be this value, which is 0. 0, 0, 0, 0, 0 on all the bits. Otherwise, if we're not in reset, I've said that the next value I want for the state, or in other words, the next value I want on the Q output of the D flip-flops, is this variable. So this is the key to the whole state machine, is how this one-wire state next gets calculated. And the way that gets calculated is in this next always block. This is where the guts of the state machine is. So let's look at this always block. This is just a big always block. Goes all the way down to here. And you'll notice one of the key things about it is there are now these were non-blocking assignments. Okay, these will get turned into flip-flops. Okay, using non-blocking assignments. You notice in the state machine itself they're all blocking, but there are absolutely no delays in here whatsoever. And so this whole state machine gets turned into pure combinatorial logic. Okay, and how does it do that? Well, notice that we have a case statement at the beginning. The case statement is going to be used based on our current state, the output of those flip-flops, OW state. So here I said case OW state. So when we start off, we're in idle. Okay. So during idle, that D out pin, we're just starting up from reset. So we're right here. We want this D out to stay low, and we're going to want it to stay low for this amount of delay time. So let's go back down here to our state machine. So the first thing I do is it's going to stay here as long as we're in reset, remember? Okay, if we're in reset, it's going to stay in idle no matter what. But as soon as we're out of reset, then this thing starts to move to the next state. So I said that the next state is going to be OW delay, this one. Okay. So now, when the flip-flops clock on the next rising edge of clock, it'll clock into the cues, it'll clock in that next state, which will be OW delay, which, remember, I have values for, which is 1 up here. Okay. Then, what's going to happen? Okay. So on the next positive edge of clock, the state will actually go to OW delay. So now when we're in that state, it's going to calculate an OW state next based on the current state. So now we're in OW delay. So if we're in that state, the only time that we're going to go to the next state here, OW frame, is when our delay counter has counted all the way up to that certain amount of time, and that's what this num delay clocks is. Now num delay clocks is just a simple calculation. It's I said this delay time is in milliseconds. So if we take the clock frequency and we divide by 1,000 and multiply it by the delay time, that'll give us the number of clocks based on this frequency that we need in order to get this number of milliseconds of delay. So it's in this case, it's a fairly large count. So we go back down here. So this delay count, if it's not equal to num delay clocks, it stays in this state, because I've said OW state next is equal to OW delay, the same one we're in. So let's take a look. Let me give you let me give you an idea of how that. I'll just kind of draw this. Let's say we have 1, 2, 3, 4, 5. There's our 5 flip-flops. Okay, I didn't draw very good, but get the idea. Okay, these flip-flops, they all have Q outputs. Okay, and they all have a D input, and they all have a clock. That's our clock. Okay, so each of these have a D input. Okay, and then I'm going to just call this our logic, our combinational logic, and that's from that always block that has the case statement and everything in it. So basically, these feed into that logic, which is all just and OR type gates. It reduces down to, and then this comes back out. Just a sec. Let me draw this. This connects in. Okay, and the direction here is this direction for all of these. The direction here is this direction for all of these. And then we have other inputs. Okay, and they may be 1 or more bits. They could be multiple bits, like the data count or any other signal coming in. Okay, so this is the let's see if I can do this. I'm not very good at this. This is our state machine logic. Oh. Okay. So that's our state machine logic. So this is what it's actually turning into. So this set of lines right here, this 5, I can't draw, but anyway, that's a 5. This is the OW state next. Let's go back to our this OW state next. That's what we're calculating to feed back into those flip-flops. So anyway, when we're in this state, we have to wait for the delay count to count up. Well, somewhere we need to initialize that delay count, so I actually do that up here. Let's see where that is. Here's the logic for it. I said if I'm not in state O delay, then I'm going to clear the delay count just to make sure it gets set back to 0. So if we're not in OW delay, it gets set to 0. If we are in that state, then this counter keeps counting up until I get up to num delay clocks. So if delay count is not equal to num delay clocks, I just keep incrementing the counter. Okay, so this counter, that's the logic for this counter, and you see that it's based on my state machine as to when it clears and as to how it counts and when it counts. And so this too is flip-flops, and it's however many flip-flops delay count right there, that many bits, DS bits total. And DS, of course, was made from this num delay clocks. So I have to count from 0 to num delay clocks minus 1. So that's where that comes in. And there's similar variables in here for doing all of this logic. B count, XD, data count, these are other variables I use. And they're all based upon that state, OW state, and any other inputs or conditions. So once the delay time is over, the next thing it'll do is it'll just go to this frame state. And in this state, I basically don't do anything, but I do use it in some of my logic up here to determine certain things, like when to clear certain counters. So basically it's in this state for just one clock, and then it goes on. Okay, so it goes to this OW sync high, and so basically this state, it's going to stay in this state for the first quarter of a cycle, and it's going to put out a high on the D output. So let's go back up here. See, for this first sync bit, I want to put out a high for the first quarter of the cycle, and then for the next 3 quarters I'll put out a low, and then I'll want to repeat this 4 more times. So let's go back down to the state machine. And here, the way I know when the time is up is I have another counter. I call it B count. And if it's not equal to Q1, if you remember, that was calculation of the number of clocks I need to count to get through the first quarter of the bit time. So once it counts up, then it can go to the next state, which is the sync low. Otherwise it just stays in this state and puts out a high. And then this state is similar. As soon as B count gets up to the full length of a bit, that says Q1, 2, 3, 4, then it can go on and can do other things. I think we're getting close to our time. We can come back to this and finish after the lecture, and then we can also talk about the one-wire receiver and how it functions. So basically this is how the state machine works. Any questions? Do I still have everybody?
Yeah, looks good.
Yep, no, very good.
Okay, is that starting to make a little more sense now?
Mm-hmm.
All right. Yeah, I don't think our lecture will take a real long time today, and we can come back and maybe talk a little bit more about the rest of the state machine. But I think if you follow it through, if anybody wants a copy of this one-wire transmit.v and one-wire receive.v, I could just post it on our site.
Please
I'd
do.
like to see that.
Okay, I'll post them on with the rest of the labs and stuff.
One quick question, Kirk.
Okay.
On your transmit, the Aussie board is just transmitting this sort of in the blind. I mean, there's no handshaking going on here whatsoever, right?
Right.
Okay.
Yeah. And the whole key for somebody else to be able to receive it is that we always have this rising edge every time period. Now the way that the receiver is going to know that's where the sync bits come in. Basically this delay time is to allow for any other boards out there to get reset, do whatever they need to initialize themselves, so that when these sync bits come along, they can start the receiver can actually calculate the time between this rising edge and this rising edge and to this rising edge and this one and this one. So it can go 1, 2, 3, 4 and say, okay, I have 4 values, 4 counts for each of these, and I'll just take an average of them, and that'll be my TB. Okay. So the receiver may have a totally different clock frequency, and in this case they do, because Aussie is using a 48 megahertz clock to generate all this stuff, okay, and Mercury and Penelope have the 122 megahertz clock that they're using. But it doesn't matter, because all they have to do is just calculate the number of clocks from here to here to know the time period. They don't need to know anything about the frequency that this was generated at the other end.
Okay.
So the sync bits are for the receiver's benefit, just to get ready to know when. Okay, so let's say the receiver counts 300 clocks. It takes it 300 clocks from this edge to this edge. Then the receiver knows that after this low time, when the data starts coming, right after the next low to high transition, whether it be a logic 0 or a logic 1, it knows it's going to take 300 clocks for that data. And so it can go out there halfway and sample in the middle. That was the whole idea behind it.
Yep.
So there's a lot of other ways this could have been implemented. This is just something I picked and chose to do. Okay. So now we're going to look at the bus functional model some more. Now, okay, here we have some sort of CPU interface, and in fact I think it's sort of similar to the old Motorola 68000. Anyway, in this particular CPU, we're going to look at a read cycle and a write cycle. In this one, the read cycle consists of the address changing, and for a read cycle, the read would be high. And then after some amount of time, the address strobe goes low, specifying that we've got an address ready. And then after address strobe goes low, then there's some specified amount of time where the data actually gets put onto the bus from a high impedance to whatever value we need. And also at that time, the data strobe goes low. Another one of our timings is there's a time from the data strobe going low to when address strobe gets removed again, and the address changes. Also, at the time address strobe goes high, then data strobe sometime after that, whatever this amount of time is, will actually go high too. Similar for the write cycle, we have timings in a very similar manner. And as you can see here, once the address strobe goes low, this is an asynchronous protocol. That causes a DTAC here. I called it data strobe, I think in the last one. I'll call it DTAC now, I guess. And then that, of course, going low causes this to go high, and that going high causes this to go high. Similar for the write cycle. When this goes low, sometime later this will go low, and then because of this going low, sometime later this will go high, and then because of this going high, sometime later this will go high. So let's look at how we might make a read task. Basically, we're going to need, for inputs, we're going to need an address to read, and for output, we're going to need data. And this will be an asynchronous implementation, and we want to make some sort of timing checks in this. So let's look at a little snippet of code and how we might start off doing this. So here we have a task called CPU read, and I've defined the address as being 8 bits wide. That's an input, and the output is 8 bits wide. That'll be our data that we get from doing the read. And I've declared a register called time that will be used for some timing checks that we want to do. And then we'll have our code in here. So let's look at what we might put in our code now. Okay, if we're starting off for a read, first of all, our address is going to be set. We want to set our address to whatever we're given, ADDR. So let's go back and look. See, our ADDR, we want to set it to that. We want to set the read-write line to a value of 1, right here. Then we want to delay some amount of time before we assert the address strobe. Okay, so this is our delay, and here we set address strobe to 0. Okay, so this is just a little snippet of just this portion of it. Okay, now let's look at another snippet of where we've said that we want the, after address strobe goes low, that's this statement here. Let's record the time, okay, and then wait for the negative edge of this DTAC, and then let's take a look at the difference between the time that this goes low and the time that we saved back here, stamp. Okay, so if it's less than some certain amount of time that we want to tell it, then we might print out that, hey, you know, something is wrong here. You know, it didn't meet our qualifications for the design. We might also want to do a similar thing based on the DTAC. Okay, once it goes low, that's this negative edge of DTAC, we may want to delay a certain amount of time and then set the address strobe high. And at that point, we may also want to grab the data. So this is another little snippet of something we may want to do when we create this model. Okay, so we set our data, and if you remember, our data was our output for the task. And then another thing we may want to check is after we've set address strobe high, does DTAC go back high within a certain amount of time? So when we set address strobe high, let's record our time by setting stamp equal to $time, and then we'll wait for the positive edge of DTAC, and then we'll check the difference in time to see if it's less than a certain amount of time that we've is spec'd for this particular design. And if it's not, we may do some error, print some error, do something that specifies, hey, you know, the DTAC didn't go high like it was supposed to. So now let's kind of look at some of the things that we would need to do in a write task. Okay, for inputs, we're going to need an address to write, and we're going to need the data to write. And again, this is an asynchronous implementation with timing checks that we want to have. So here's kind of the guts of our CPU write. We would have two inputs, 8 bits wide for address and data in this case. And then again a time variable so that we can record some timing for some timing checks. So here when we start off on a write cycle now, you would set the address right here would get set to whatever you're being given. Okay, address. And the data too would also get set to whatever we're being given in the task. Right here. That's what we're being given. Okay, and we would set the read-write line to a 0. And then we would delay a certain amount of time right here. And then we'd set the address strobe low. Okay. Now we're going to want to do a timing check. So at the time address strobe goes low, we're going to want to record the time, then wait for the negative edge of DTAC, and then do our checking to see, you know, did it go low within a certain amount of time or not. So this is just another little snippet of something we would need to do. And here's another little snippet of something we need to do in the task. And also at the time of the negative edge of DTAC, we want to delay a certain amount of time, and then we want to set the data to high impedance right here, and we want to set the address strobe back to high after that certain amount of time has occurred. Then another thing that we need to do is when the address strobe does go high, then we need to record that time and do another timing check to make sure that DTAC goes back high within a certain amount of times, just like we did on the read. So those are the types of things that we need to do for this. And let's assume that that's implemented. And then how can we use it? We can now perform software-like tests, sort of like read, modify, write. So here we go. So here I've created an initial statement and a block, begin block called test. And I've created an 8-bit data register. And here now I can call those tasks. CPU read, I can feed it the 8-bit address and the 8-bit data. There may be other things you do before this, but and then we can actually look at the data once that task is finished and see, oh, let's say we wanted to know whether or not it was 0, and then we might print out something based on what data got returned. Or maybe we want to modify the data slightly. In this case, we're going to modify data bit 0, and then we're going to write it back out to this address. So here you have a more software-like test that you can write by using tasks. So tasks are really good for doing simulation test benches. They're not synthesizable. This is just for using test and simulation. Now let's go back and let's assume that anything in this design could be broken. Maybe the DTAC doesn't, go. Not only does it not go change to go back high in a certain amount of time, but maybe it just plain old doesn't occur. It never goes low. So how do we check for that? Anybody have an idea? What kind of Verilog statements did we look at in the past where we're checking for things? Well, that's where the fork and join come in real handy. Okay, remember, for a fork join statement block, here we have one called DTAC OR. This block, this begin end block, and this begin end block execute in parallel, right? So, in order to get out of the fork join, what has to happen? Both blocks have to end, or the block has to get disabled. So we're going to use the disables here. And what we've done is we've said, for this block, it waits for the negative edge of DTAC. And if that happens, then it does a disable of this block, and so it would get out of it. Well, if DTAC comes along, then that's great. We would get out of this block. If DTAC doesn't come along, then this block here is executing too in parallel. And after this certain amount of time, then it kicks it out. Okay? So then we can check to see if the DTAC is low or not and determine what happened. Okay, we can check to see if the timeout has expired. So the fork join is useful in doing these timing type checks. So if the neg edge comes along, DTAC's going low, then it'll knock us out. If it doesn't come along, then this timeout will kick us out. So we're kicked out of this block one way or the other, either after the neg edge or after a certain amount of time. And we can use that to determine what kind of errors we might want to report. Another thing is, before you even go into the fork join, you might want to check and see, well, if DTAC's already low, there's no need to wait for the neg edge. It may already be low. And you may want to do something based on that. So you need to test for all kinds of conditions in order to simulate functionality, and actually to test the functionality of the device. So in Lab 8.1, I want you to learn how to write CPU bus functional models and learn how to perform read and write cycles using CPU bus functional models. So I think, in your lab you're going to have something like this. So let's kind of go through it real quick. Okay, here's a CPU interface that uses a 16 megahertz i386XX bus. And as you can see here, the clock consists of a phase 1 and phase 2 type setup. Excuse me. And from phase 2 going high, you can see that the address will change. This could be either a min, typical, or max. Anyway, there's a delay. And in this case, it'd be like 4 nanoseconds, and the address changes. Here we have the address strobe changing from that rising edge, 4 nanoseconds, read-write changing 4 nanoseconds, and then here this time is 4 nanoseconds. There may be a certain number of wait states depending on how long ready is before it's asserted low. And notice that the rising edge on phase 2, not phase 1, checks the ready. It's going to sample the ready. But in order for ready to be valid, it needs to be there 19 nanoseconds before this rising edge. Okay? That's called a setup. And then it also needs to be there for 4 nanoseconds after the rising edge. That's called a hold time. Similar for data. You've got 9 nanoseconds of setup and 6 nanoseconds of hold. Okay, so that's a read cycle. Then you have similar type things for the write cycle. Similar timing, setup, holds, different delays. So if you're making, you're going to be making a block, a functional model here, and a bus functional model, sorry. And these are the type of signals that you're going to have. You're going to have a clock, and that'll be an input, and that'll be 1 bit wide. Okay, you're going to have an address. It's going to be 8 bits wide. You're going to have the address strobe and the read write and the ready. Those will all be 1 bit wide. And the data ready or data accepted, that's the one that introduces the wait cycles. Okay, depending on when it gets asserted. And then you're going to have a bidirectional data bus of 8 bits. And this will be your register map that you'll have in your lab. Is basically just 2 addresses. Address 0 will be what we call a status register. You're going to make a status register, and address 1 you're going to make a mask register. Okay, so it's going to be sort of an interesting lab for you, hopefully. Let's talk about observability now. Sometimes it's necessary to look at internal signals in your design, not just the very top level signals. And currently we've observed signals through the pins of the top level module, but we need a mechanism for improved observability so that we can actually maybe look at signals down in the design. Okay, so let's say we have a test bench, and in that test bench we've instantiated a module, but that module is a hierarchical type module, and in our test bench at the top we want to be able to access something way down the hierarchy down here. We want to look at it. So we want to observe, say, a particular signal or test a certain signal. So how do we get to it? Well, one way is through the module pins. You could put that signal in the module pin list and bring it back up through each module. Okay, but that's going to be a high maintenance thing because you're going to have to insert them in, physically edit your files, put them in, and then when you're done, since it's not something you need, it's just something you're testing, you're going to have to rip it back out. And so it's a lot of high maintenance. So the language actually provides a hierarchical type access, and that's what we're going to look at. One thing to remember is that it can't check the correctness of the hierarchical name at compile time. So you may compile just fine, but then when you go to simulate, say like you're using ModelSim, you'll actually get an error at that time because it'll say, hey, I can't find this. What are you talking about? Okay, so don't expect the compiler to actually be able to check it. So a hierarchical name is similar to full path name in a computer file system. Hierarchies are separated with a period. Things such as instances, blocks, and task names are like directories. Registers and wires are like files. And the name of the top level modules are like roots. And names can be relative to current module instance. Okay, and there's no equivalent to a ... like you have in Unix or something. So let's look at how this works. Here I have a top level module. It's called top. And you see that I've instantiated 2 instances of the same FIFO, but I've given them different instance names, one called in, one called out. And then here's the module FIFO, and in it has a wire we'll call W, and then it has another instantiation of a module called RAM with an instance name of buff. And here's the module RAM, and in it, it's got an initial block, let's say. There's going to be a lot of other stuff, but these are just some of the things in it. It's going to have a begin-end block that we've named B, and then a register inside of that called R. So here's our structure. We have top, and then we have our in and out FIFOs right here. And then within each of those we have a wire W, and then we've instantiated the module called RAM, which we've called buff. And then inside of it, the begin-end block B and register R. So that's our structure. So how do we access something like the wire called W within the in FIFO? Well, here's an instance of another module we've thrown in called, we'll call it side. If I wanted to access that, I could say top.in.w. Okay, and in the module top, let's say that I wanted to access this register down here in the out FIFO. So I could say out.buff.b.r. That's how you would get down to it. And that way there's no need to bring that particular signal up through the pin list of each of the modules. So that would access it directly. So you might have some other register that you assign equal to this, or you might do some test of this to see if it's some value. Anyway, but this is what you would use for the name. Okay. And here's another example. Here we're in the module FIFO, and I said buff.b.r. Well, that could be either this R or this R, depending on which FIFO it was that we instantiated up here. Okay. So in Lab 8.2, I want you to learn how to use hierarchical names and learn how to bypass interfaces for additional visibility. I'm going to talk more about full timing simulation now. So let's say we're wanting to...
1 second.
Okay.
Back like about 3 slides or so, I lost the connection for just a brief period of time, so the recording won't have it either, from what I can tell. But it was the slide about is this synthesizable, the way that you can access nodes all the way down? I mean, it's probably not.
It's not
advisable, but can you?
It's not. This is not something you synthesize. This is something you're going to use for observability, for testing for your test benches.
There's been cases, that in some of the FPGA stuff that I've done, that there might be a timing issue inside the FPGA, and it would be useful to, bring out a signal internally, on a live FPGA. Would you be able to do it this way?
No, this is not. Well, what you typically do in the live FPGA is there's a couple different ways that you can actually do this. For Altera, they have a thing called signal tap. And signal tap actually inserts some extra logic in with your logic so that you can observe certain signals and you can actually capture them. And then through the JTAG port, you can read them out and you can see what it captured. Basically, it uses like an internal FIFO, and it just captures a FIFO's worth of data with the clock, and then you read that back out onto your screen, and you can look at timing waveforms. I'll show you that sometime. That would be good for a demonstration. So that's one method. The other method,
can you actually bring a signal all the way? Yeah.
Yeah, the way you bring it. I don't think you can. I'm not sure that you can use this. I don't think it'll synthesize. I'd have to check. You can either bring it up through the pins if you needed to, or typically you'd use like signal tap for the Altera parts, or for Xilinx they have one that's called chip scope that does a similar thing. Or you would just take that pin and bring it out to another pin on the FPGA. I mean, you take that signal and bring it out to a pin.
Yeah, if you do that, then it looks like you got to like go through, pull it all the way up through the modules.
Yeah.
That's why. if you could access it directly, then you can put it right to the pin.
Yeah, the preferable way to do it, like with most of these things now on the FPGA, is to either use like the signal tap functionality or the chip scope for Xilinx. That allows you to look at what a bunch of signals actually, not just one. You can pick a whole bunch of signals and look at them that way, and you get like it looks like a logic analyzer because it'll print out on your screen, waveforms. Typically, you're not going to want to just have one signal when you're debugging something like that. You're going to want a bunch of signals. So, yeah, I've never tried to use this for bringing a particular signal out. I don't think it'll do that. But this is very good for simulation. You want your simulation to first be able to functionally check that your design is working, and then we're going to talk about timings. That's what we're fixing to talk about next. But there are cases where you actually want to see, you've gone through all your timing analysis the tool has that you're using. You've gone through all your timing analysis. Everything appears to functionally be working in your simulation, but yet the design doesn't work. And that's what you're talking about. And that's where the chip scope and signal tap comes in really handy. I need to show that sometime so you can see how that works. So let's talk a little bit more about timing and timing models. So you could model your logic gates using some standard delays, and that might be good enough for a rough timing simulation. So let's say you have an AND gate with an A and a B input, and it has some type of load, capacitive or some wire load out there. And in this case, we've modeled it with a rise and a fall delay. And here's our AND statement. So this is just sort of a rough timing simulation. But we may want to get more accurate. So in order to get more accurate, we need to know things such as the load on the output, and maybe the length of the wire in the device, like if you have an FPGA or an ASIC, and what they call the wire loading. And different instances of the same module can drive different loads. Okay. So in the case of this, okay, here we've just said that in general all of these AND gates have the same load, they have the same rise and fall. Well, that may not be true. For a rough timing thing, that may be alright, but in real life it's not going to be, because in an ASIC things are used with different loads and different wire lengths and everything. Okay, so delays are instance specific. And so you can't really hard code them if you want an accurate timing model. So the solution is what's called special parameters, and special parameters are overwritten by an external delay file. So I'm going to briefly touch on these special parameters. I'm not going to go into any real detail on these. This is something that you can look at and cover on your own if you're really interested in knowing how to create these accurate timing models. Okay, there's what's called the specify block, and in that specify block there are things called spec params, and so it could define a delay from the A pin to the C pin of being 2.2 for rise and 3.4 for the fall, and for the B pin maybe it defines them a little differently. Okay, and for pin-to-pin delays it may use those spec params that were defined here. These, however, can be overwritten, and I'm going to show you that in a little while. But if you want to go into how the specify block and all of these spec param stuff work, you're going to get to do that on your own. Okay, we're going to rely. You're going to rely mostly upon the vendor's tool, such as in this case Quartus, the Altera tool, to actually create all these timings and stuff for you, and to actually check them. And I'll show you more about that later. So in order to get accurate delays, you need some sort of an external delay calculator, we'll call it. Okay, that external delay calculator is something that the Altera tools can actually do, or the Xilinx tools. They can do that type of thing because they know about their parts. And they can calculate those delays based upon the loading of the gate. Say, like in this case, this gate, you can see it has a wider fan out than this gate over here, you know, and the loadings can be different. Also, what we call the wire loads, they can become a dominant load factor. You know, like you're going on the FPGA, this may be a short path with a certain load. This may be a longer path to another gate with a certain load. So the delays here can be very different. Okay, this is just a, I'm just showing you kind of a simple RC wire load delay model. The ASIC or your FPGA tools can produce what's called an SDF file. And it can do that at various steps in the implementation process. And the degree of accuracy...
I'm sorry, I can't do it.
Hello?
I gotta do this, too.
Okay. The degree of accuracy increases with the level of details. So if you don't run it through the tools, other than you just running simulation tests, the default is there's no SDF created. And so let's say in your module you had something where you said R equals R1. Well, there wouldn't be any physical delay to that. I mean, this all happens at the same time. So you would just see R become the same value as R1 all the time with no delay between them. However, after floor planning, you know, this R might be physically, you know, one side of the chip than R1. So in real life, there's actually going to be some delay time difference there. You know, if it's got to travel across the chip, even though those chips are really small, there's still some time associated with that. So you'll get increasing accuracy as you go through each of these steps, like floor planning, after post-synthesis, after you do a placement, and then after you do a route. Okay, it'll increase as we go down the steps. So these accurate delay values are stored in this SDF file, which is a standard delay file. Instance-specific delay values are back annotated in the simulator. So after you've compiled and you've done all your place and route and those type of things, the delay calculator can create this SDF file, which you can use in your Verilog simulation to get a much more accurate timing model of how the signals are going to look. Okay. Typically, well, no, I'll talk about that later. Here's sort of the process that you may go through for creating an ASIC, let's say. So for Verilog, I mean, we're going to create a real part now. You're going to use RTL code. So you create an RTL model. You may start off with a behavioral model just to get yourself up and going in simulation to see that, yeah, this does what I want it to do. And then you may turn around and replace that behavioral model with a real RTL model that's going to synthesize real logic. So anyway, we'll say we start off with an RTL model. You can do a functional simulation, and the functional simulation is, we don't worry so much about the timing and the delays as we do that the thing is just functioning properly. It looks like everything is working correctly. And when that's happening, then you're at a point where you could actually synthesize it, and you could get a gate level model. It'll turn it into real, you know, flip-flops and 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 OR gates and all that kind of stuff. And at that point, you could then take that model and you could do another functional simulation, make sure things are okay. You could run it on down through the place and route and layout and get a standard delay file, and then use that in conjunction with your model to actually do both functional and timing simulation to make sure it's still working even after you know even after it's calculated all the delays. We want to make sure that it's still functioning. And the FPGA may be the same process, or it could be a little different. Some of them may actually create from the RTL model. They may create what they call a primitive net list, such as Xilinx, and it saves it in this .xnf format file. And then you could create a gate level model and do the same type of things. So this is basically the same as the last one. So the SDF file actually annotates pin-to-pin delays, interconnect delays, and timing constraints such as setup and hold and pulse width. It can check all of that kind of stuff for you. So that's where you have to rely on the vendor tools to do a lot of this for you. You're not going to be making, if you're designing an FPGA, you're not going to be designing all the timing models, because they're going to do that for you. Okay, but if you are a Xilinx vendor and you're needing to create models for the delays, then you might have to be writing Verilog. If you're working for Xilinx or somebody where you're creating models for this kind of stuff, that's where this would come in. You can use the $SDF_annotate system task to back annotate simulation, and it's normally done at time 0. And it can be done at any time if you use this particular option. So here's the syntax. And then here's an example of how it's used. Okay, so this is our device under test, so to speak. And there we can create that. So in 8.3 you're going to, and you can do this optionally, you can learn how to back annotate a gate level simulation using an SDF file, and you can learn how to interface to a third-party FPGA model, and you can learn how to program a LMG smart circuit FPGA model, and learn how to alternate between simulation configurations. So this is sort of an optional exercise, I'll call it. Okay, so that's it for today's lecture. It looks like we have 2 more lectures left before the end of the series. We're going to start talking a little bit more about RTL coding, and so that's why I'm going to start talking to you more about the actual code here now, is because you're kind of getting to that point. So before I go back to our example code here, do I have any other questions? If not, I'm going to get a drink of water. Okay, would everybody like to go back to looking at our one-wire transmit and receive stuff?
Sure.
Okay.
Yes, maybe move on to the receiver.
Yes, okay. Let's go ahead and do that. Let's go ahead and move on to the receiver now. Okay, for the receiver, basically we have the same information here. But for the receiver, I have a reset signal coming in, a clock signal, the received data, which is an output, okay, and it's data bits wide, and a receive ready that says, okay, we've got new data, and the 1-bit signal, which we're bringing in from the transmitter, called DN. I should have changed that here. Here, this is code in progress. Save. Okay, so here I have some parameters. Sync bits, by default is 5, and that's like in the transmitter. Okay, and I'm just going to leave it at that for the default. Could reduce it or increase it if we wanted to for some reason. There we go, 5. And I said my default for the number of data bits is 64. Okay, and this other parameter, I'll talk about that later. So, based on data bits again, so let's assume we had 64. So if I wanted to make a counter that counted from 0 to 64 minus 1, I would need a register that was this size, and that's what that function again calculates. I put it down here at the bottom of this module, so it can determine how many data bits. And then I have some local registers that I'm going to use in the code here. I've just created some various ones. And then my state machine, for this particular module, I need 2 bits. Okay, so this is my state, and this is my next state. And then I've created a register that's 16 bits wide and 4 deep. So I've created 4 of these, 16-bit wide. Okay, so what am I going to use that for? I'm going to use that to record my sync bit timings. Okay, so I'm going to record, I want to know, oh, excuse me here, there, save. I want to record the time from here to here. That'll go in that in the first register, then the time from here to here will go in the next one, and so on. So I'm going to record those 4 times, see how many clocks it takes. Okay. Now, in general, here I have an always block that's clocking on the positive edge of the clock. Now, there are some flip-flops that'll clock on the negative edge. So you can do that if you wanted to, but it's typical to use the positive edge of the clock, because what's inside of this always block, this module is written in RTL code, which is a subset of Verilog, so everything in here gets turned into real physical hardware. So everything in this always block is written in such a manner that these signals, all these different ones, are flip-flops. They become flip-flops, D flip-flops. Okay, so you can see there's several.
Question.
Okay.
Just looking at that code, can you make that statement? I mean, how when I see that, I wouldn't know whether that could be turned into flip-flops or anything else.
Okay, we're going to talk more about it, but the way that I've structured and written the code is what determines that it gets turned into D flip-flops or flip-flops.
Okay. And principally, it's because you're using non-blocking assignments here. Is that the idea?
Yes, they're non-blocking. You use non-blocking assignments. So you use always at some clock edge. That's the first thing, and then I use non-blocking assignments. Okay.
Gotcha.
Now there is one thing you'll notice in here, and I want to point this out. You'll see that I have this delay thing here. This doesn't get synthesized. I use this merely for simulation purposes, okay, to give me some rough timing model, okay? That's the only purpose that this value is here. And I've defined this TPD up here at the beginning to be 1.3 nanoseconds. Okay, so it's just a rough timing model. And the reason I do that for my simulation purposes is so that I can see that, okay, there's a real physical delay from D to Q. And so when I see a clock edge and I see D to Q change, if I didn't have any delay and it were exactly on top of the clock edge, I might be curious, well, did this really happen just before or just after, or, you know, what actually happened there? It's a lot easier to see if I have a slight delay after the clock edge that, okay, yeah, it's because it's a clock to, it's a clock to Q output delay. So that's for this TPD. I'm only using, I just call that my typical prop delay. I just stick that in there merely for simulation purposes. The for RTL code, it ignores this completely. Okay, so anyway, all of this stuff in this particular always block, because I have the at pos edge clock and I'm using non-blocking, these are flip-flops. These become flip-flops. And then again, this always block, now this is a notation you can use. You could say at and then parentheses and list all the different inputs and things that might change, such as the dB rise, the TB state, the resync, whatever variables I'm using in here. But you can use this shorthand notation, and then you don't have to list them all, because when you're changing your code, you might change, you know, for a while maybe I got resync in here, but maybe I take it out and put something in. That way you don't forget. You don't have to worry about changing the list all the time. So this is a much nicer notation now that they have that you can use. So any change in any of the variables coming in here, anytime they change, then this recalculates. So here we have a simple state machine, and you'll notice in this one they're blocking.
Question: how do you know what's included in the any?
Say that again.
So in other words, how do you know what the asterisk refers to?
The asterisk refers to any of the signals being used in this block. Anytime any of them change, it'll actually go back through here again. So remember that we're using an at. So anytime any of the signals in here that you're using, anytime they change, then it comes back through the block again for simulation purposes.
Maybe another way to ask a question about that would be, once you finally get your model finalized in your own mind, would you go back and change that asterisk to be a finite list of variables?
No, you could do it this way, where you list all your signals in here, and then you close it with a parentheses. But, these might constantly change while you're changing the design, and it's sort of a pain in the butt to have to, go and constantly change this list all the time. So instead, you just get rid of the list, and you do the star, and that's the equivalent. Much nicer.
But in your final design, you would have a list, or you would not?
No, this is the final design.
Oh, okay.
Yeah, if you want to put the list in and do it that way, that's fine. But you have to make sure you've got all the signals in there. Okay, but
yeah,
I like this notation.
In practice, this would be the easiest way all the time.
Yeah, this is the way I always do it because it's much easier to do this now that they've allowed this in the language.
Gotcha.
So I like this. So then I just say always at and then star. And so basically this whole block, it's not running on a clock or anything. This whole block right here just gets turned into and or gates. And that would be, oops, sorry, let me bring up, that would be this block here. And this is all, like I say, just, and or gate type things, gets turned into just pure combinatorial logic. Okay, so in the state machine, you're feeding it basically the output of the flip-flops. Okay, that's the current state. The current state is the value that's on these output flip-flops, the Q output. Okay, so that feeds into the state machine logic, that combinatorial logic, that always block where we did always at star. And then that gets turned into just pure combinatorial logic, which is based upon any of the inputs coming in, and then it creates the next state bits, which go to the D inputs. Does that make sense? Hopefully.
Yep.
Okay. So in this state machine, you can see I only have 3 states: idle, TB bit, and next. And then I also put in a default, so that for some reason, if it powers up weird, it does something funny and gets off in a wrong state that's not being used, it'll force it back to idle. So this is always a good practice to do, is to put in the default. So here so the common thing that you see in each of these is, first of all, each of them are based upon the current state, which is the current output, along with different inputs, okay, such as this signal or whatever. And then they produce the next state, which is going to be clocked in to the flip-flops right here. TB state equals TB state next. And that's about as simple as you can get it. And this method for doing state machines and stuff works very well. I've never found I can use it on different vendors and different people. There is another way that you can do some state machine stuff. I'll show that sometime. But I like this method the best.
Question?
Okay.
Yeah, this is Joe again. If I'm still trying to understand this this at star significance, because I remember seeing some code earlier where you had this long list of input outputs, and so does the at star only work on a state machine, or and the other things that I was looking at earlier, where you had this very long list of input output signals and pins and stuff, you did that and did not use the star on that. So is there a distinction there, or what?
No, I'm just showing you different ways.
So you
Okay.
could have used an @ star with those as well?
Yeah, probably. Yeah, I think so.
Okay.
Yeah.
All right.
I mean, let's take, for example, let's say that I said always at resync. Now, what does that mean? Always at resync. How would this always block execute if I did this?
Only if resync changed, I guess.
Yeah. Any change in it, whether it goes high or low or whatever, just as long as it changes, then that allows it to come back through the always again, right?
Right.
Okay, if I don't list some other signals like dB rise, it's not going to come through when it changes. So you're not going to get a
Right.
true simulation, right,
Yes.
of how this block works if you don't list all the signals. Okay.
Yeah, I guess my reiterating my understanding. I'm trying to understand this.
Okay.
If you there are some instances in your code, and I'm not sure where it was, but I remember seeing long lists of input output names where you, if I understand the star stuff, you could have used a star there and not had that long list of names. Is that right?
Yes.
Okay.
Yeah. The reason I showed you that is the way that you have to do it for the older the Verilog 95 standard. The newer standards, like the Verilog 2001, you don't have to do that anymore. Okay. But I want you to know that that's the way that, some of the older ones, I don't know if you should ever run across the older, versions, but that'll work in all cases. Okay. So I could have written it like this right here. And that would make make it work the same.
Okay, that makes it clear.
So ever since they said I can replace that with the star, I've done this. Okay, so now I'm telling you about the new method.
Okay, but you have examples of the old method in various files.
Oh,
that
yeah.
You showed us.
Yeah, and I want you to do it that way for now.
Okay.
Okay, but once you're done with the labs and everything, and you go ahead with the lab. Go ahead and try the star, if you want. I just want you to know the basic Verilog syntax, and there still may be some of the compilers out there that may not like the star. I think most of them by now, will take it. They're up to the 2001 standard. For a while, within the last few years, not everybody was up to the 2001 standard.
Okay, that makes sense.
Okay. So that's my preference now. I really like it. So yeah, it may make you do some things that are old school for a little while, just so that you appreciate the new stuff.
Well, it's all new stuff.
Okay, yeah, it's all new stuff. Anyway, I think you still need to know about the other, just so that you understand what this star is really doing.
Yeah, well, that helps. Thanks.
Okay, so this particular state machine, there's only 3 bits. And so the first thing I do in idle, well, of course, we go back to our flip-flop here. Let's see, there, TB state. And I've said that anytime we're in reset, it's always going to stay in idle. I don't care what's going on with the rest of this logic down here. I'm forcing it to stay, in idle state. So now once the reset's gone, the TB state will be whatever the TB state next is. And this is just the way I kind of do it. You can put whatever you like here. You can put some other name or whatever. I just like to put the next because that's the next state. So here, once reset's gone away, then what we're going to be doing is we're going to be looking for this signal called dB rise. And if it's true, then I'm going to go to the next state. Okay, so what is this dB rise? Well, this is the beginning of a data bit or a sync bit. So how do I determine this? Let's go look for dB rise. I'm going to show you a cute little trick. Okay, so let's look at our signals again. So what I'm wanting to do is I'm wanting to determine, how do you determine when you have the rising edge of a signal? Do you know how to do that? I'm going to show you how to do that. Okay. Let's...
At pause edge.
Well, This is not a clock. This is actually a signal. Okay, you're running on a clock. The state machine is running on, and in this case for the receiver, let's say that the receiver is over in Mercury. Okay, it's got a 122 megahertz clock, and so your state machine, your flip-flops, the clock to the flip-flops is running on that 122 megahertz, and this is a signal coming in a pin, and you're going to sample this signal. So let's assume that the clock speed is much greater than this pulse width here, okay, which it is. So here's how you can do that. Let me see if I can draw this. File, new, no. Okay. So let's say that let's just say that I have a signal that changes. Okay, there's a signal coming in a pin. Okay, maybe it's that pulse we're going to look at. Now I also have a clock. Okay, that's pretty, isn't it? I can draw. Okay.
Like a 5-year-old.
Yeah. Okay. As my wife calls them, I draw wiggly lines. That's what I do for work. So now let's say that I had a D flip-flop. Okay. Now here's the clock. We'll call that right here C. This is C. Okay, and this is my signal. Okay, and this is the D input, and this is the Q. Okay, so now we'll call this Q1. Okay, so Q1 in real life here would look like this. And then this edge where this, there might be some delay here. It's going to come up. It's going to do like this. And basically it's going to go like that, right? Does that make sense?
Yeah.
Okay. So now what happens if I do this? Okay, same clock. I feed it through this. Well, this is Q1. Now let's draw Q2. Q2 comes along. Oh, that was bad. And then it'll go down over here. Oh, I should have done this a little differently. Anyway, it'll go down on the next clock, okay, because this clock edge determines that. Right? So this is Q2. Now, here's what's interesting. Assuming this is a high-speed clock, okay, I mean, the clock this clock is faster than this pulse here. Notice that if I take Q1 and or I could take Q bar, but anyway, let's say I AND this with the naught of Q2, what do I get? I get R right? So it's Q1 ANDed with the naught of Q2, and I get this pulse. Well, that's nice, because now I know where the rising edge occurred, basically. Okay, what happens out here is still going to be low forever. So anytime this signal comes along, I'll get this one clock-wide pulse, and I'm doing a synchronous design, so everything's based upon the clock. I get a one-wide pulse. So that basically tells me where the rising edge is. Now I could do a similar thing if I want to do a falling edge. So for the falling edge, you would have Q1 let's say Q1 naught. I'll put that on the AND gate here. ANDed with Q2. Okay, now it could be your falling edge pulse. So now let's go back. Okay, so this pulse width is much wider than one clock. So in reality, like for what I'm doing right now, this the width of this whole cycle here may be like 300 clocks. So the width of this is quite a few clocks still, 75 clocks, right? So I get a nice little pulse. And here's what I do. I just declared, I said D0, D1, and D2 are registers. And then down here, on reset, I clear those 3 flip-flops. And then basically I just shift DN goes to D0, D0 goes to D1, and D1 goes to D2. So that's just kind of like I was doing here. Go back to here. This would be like D0 and D1. Now I added a D2, and the reason you do that is for something that's called metastability, in case this signal is not synchronous to this clock. If you don't, you'll get what's called metastability issues, and I'll go into that at another time. So basically, I put in a third stage. Okay, so instead of using, I use the last 2 stages so that I don't have metastability issues. So it just introduces another clock delay, but it saves you some other problems. So anyway, it does the same thing. Let's go back to the code. So there I just made those 3 flip-flops. Okay, remember this is the concatenation operator. So what gets assigned to D0 here is the DN. And D1 gets assigned, the input for the D1, that's the Q output basically. The D input gets assigned this D0. So the D0 goes to D1, D1 goes to D2. So that's, I could have written this as 3 separate if statements if I wanted to. So the first one would just say D0 gets assigned a value of 1 tick B0, and then D0 gets to assign the value of DN. And then for the second statement I'd have if reset D1 equals 0, else D1 equals D0, and then so on. So I would do the same thing. Does that make sense to everybody? May have to try some of this in simulation to see it.
Comment, Kirk.
Okay.
Hey, Kirk.
Clearly, I mean, since you went through all this trouble to do this kind of a step, that illuminates a misunderstanding on my part, because I would have thought that you could have done that very simply by using a statement like at pause edge, instead of saying clock, say Q, the Q output, you know, but that doesn't work apparently, right?
Well, no, actually, okay, no, I know what you're talking about. Let's go back. Yes. So what you would be doing in that case is you would be doing, you would be taking, you're talking about taking this Q right here, or this Q1. Yeah. Okay, but what you do in that case is when you do that, then you're tapping that off and you're running that into a clock input. Now you can do that, but when you don't use the same clock for all your flip-flops in your FPGA or groups of flip-flops, the tools can't calculate it can't do a timing analysis on it for you. Okay? It can do a timing analysis when you have them like this, where you're using the same clock. But as soon as you do this type of thing, you can do this, okay? It's not recommended, and there's a lot of reasons why, but I won't go into them. Basically, you should stick to purely synchronous designs when you can, and only resort to this if you absolutely have to.
Okay.
We haven't really covered that, but there are things known as metastability issues. Plus the tools can't give you they can't do a timing analysis for you, and you want them to be able to do a timing analysis to see that you've met timing. And by timing analysis, basically what they do is they know that, okay, all these flip-flops here are using the same clock. They have timing models. They know what the clock to Q output delays are. They know what the loading is on this signal. They know what the setup time is for the next flip-flop, and they can calculate, you know, and they know the routing, the place and route after you've routed it. They can calculate all of that information and make sure that that time from clock to Q plus the delay across the net due to loading and all that type of stuff, plus the setup time from D to the next clock, they can calculate and make sure that all of those times added together are less than the clock period. Okay? And if they are, then your design meets timing analysis, which is a very good thing.
Okay. Well, that's a subtlety that isn't obvious. At least it wasn't to me. So I'm glad you mentioned that.
Okay. Yeah, I'll talk some more about this, but I think I'm running out of time here now. But unless you can do this, like you mentioned, you can do that, but I don't recommend it.
Okay.
Unless you really have to. It's best to stick to running as many flip-flops on the same clock as you can, so that the tool can give you a timing analysis, and you'll know whether your design meets timing based over temperature and voltage and all of those type of things, and the lot that the FPGA came out of, the silicon lot. It can calculate all of that stuff for you.
Okay.
And you get into some real messy timings if you do stuff like this.
Okay.
So you want to be able, that's one of the things you want to be able to do, is meet your timing analysis. So anyway, this dB rise, real quick, is basically I take the D1 and AND it with the NOT of D2. Okay, so let's go back to our little diagram. That would be basically this D1 ANDed with the NOT of D2. And I actually run that back in through another flip-flop, so that actually, instead of coming out right here, it comes out 1 clock delayed right here. But this R is then right out of a flip-flop and not out of the AND logic, and that helps for meeting some timing thing. You can do it either way, but I do it this way a lot. So basically all I'm doing is generating a 1 clock wide pulse. Okay, and now this 1 clock wide pulse is in sync with our clock, and it can be used by other logic running on this same clock. Okay, so that tells me that, okay, I had a rising edge there. And so this pulse now will occur every time I have a rising edge, right? I called it dB rise. dB rise. I can't write with this. Okay, so dB rise now tells me when the rising edge occurs. So now I go down here, and in my idle state, as soon as I see a rising edge, and remember reset's finished, and the transmitter is going to transmit a low for quite some time, so I've had plenty of time, no problem in this particular case. So when that first rising edge comes along, I say, oh, hey, I've got a data bit or a sync bit now. And I go to this next state called bit. And then, I don't know if Michael has any more time for this, but we could continue this next time and talk about how it grabs the data.
Good.
Okay.
Okay.
All right, I think that's it for today. And like I say, I think we have just 2 more basic lectures.
Okay, great. The next meeting, do you want to meet a little early again as well?
That's up to everybody else.
It's
I
helping
enjoy
a
it.
lot. I would personally recommend it.
Okay, we'll do that then. If that's okay with Michael, we'll meet at 3:30 again.
Okay, I'll schedule it for 3:30. Okay, thanks. Thanks, guys. Bye.
Okay, thanks a lot. Bye.
Bye.
Okay. Good night, all.
Good night.